Okay, so how should I introduce this topic of fibrations? I could say something like fibrations are fundamental for understanding logic and for understanding language and for understanding how mathematics is structured. I could say that fibrations appear all over category theory to organize the different concepts, but that's not really why I made this video. The honest truth is that I just think that fibrations are very, very beautiful. And so I wanted to make this video to introduce the ideas as simply as I can, because I think that fibrations are a funny thing. The definitions involving them are pretty abstract. And because fibrations are so powerful, and because they involve so many things interacting, it can be challenging to wrap one's mind around the original definition of a fibration, especially the way that the topic is handled in a lot of books, where one simply goes straight to the definition and it's like, okay, I've read the definition, but I still feel like I don't really understand what they are. This kind of thing can happen. So I wanted to make this video to try and explain what fibrations are in an intuitive sort of way. And so I'm going to start very simply, and I'm going to sort of build up the levels of generality until we get to the proper definition of fibration. And along the way, we're going to see how fibrations interact with loads of things in category theory, and they always seem to do it in a very visual way, which I find really, really pleasant. So to give a very simple example of a fibration, let's think about this case here where we have these two elements here, B1 and B2, and we have this set of elements over B1, 1, 2, 3, and this set of elements 4 and 5 over B2. And so the idea here is that as we vary our elements in this set B, we have this sort of set which lies above that element. And we call such a thing a fiber. And then what we can do is we can kind of change perspective, and we can collect these fibers together into this sort of total space that we could call E. And then we can note that there'll be a function from E to B, which we could call P, which sort of recovers the information about these fibers, in the sense that if we look at an element of B and we look at the things that get sent to that under our function, that will be the sort of fiber over that element. And so this is the basic idea. We think about some kind of a fiber, which might be a set or more generally a category, that sort of lies above something, and it's a sort of variable fiber. It varies with the element in this base category B, and then we sort of collect all those fibers together and sort of glue them together to form this total space, and that comes with this map, which is going to be a fibration or perhaps an opfibration. We'll get to that later. So this is the basic idea, and in a sense you could think of it as a sort of generalization of the idea of a function. I mean, a function is what I'm showing in this example, but we're going to get much more general. Now, the thing is that so many ideas in category theory are organized in terms of these sort of fibrations. And often when you look at other data structures in logic or type theory, or even in language, you find fibrations there as well. They seem to be a sort of natural way of organizing things in layers. And it's really very interesting how this works. And we're going to encounter some extraordinarily interesting kind of structures today. So for example, imagine that for every set, we have a fiber over that set, and that is a category. And for every function between sets, we have a sort of functor from the fiber category over one set to the fiber category over another set. So we have this immense amount of information, and then we sort of attach it all together to form a giant category. And it has this sort of projection functor back into the base space. These are the kind of structures that we're going to think about. It's very, very interesting. And the thing with fibrations is, yes, the definitions do get somewhat elaborate. And in a sense, what we do with fibrations is to collect together lots of information into one big structure. So there does come a point in the sort of theory where all sorts of concepts seem to emerge at once, and it can be a little bit overwhelming. But once one sort of adjusted to it, it's really very easy to think about fibrations from that point on, and it really gives one a new kind of perspective on mathematics. So it's very worth thinking about this. And so I really hope you enjoy this video. Now, in this case here, everything's very simple. Our base space is just a set, and our total space is just a set. So as we vary the elements in the base space, the kind of fiber above that is just going to be this set of elements that get mapped to that thing under P. But notice that there are these two different perspectives on what's going on here. One of them is this kind of perspective where we've collected together these two fibers here into this big kind of total space, and we have this sort of map that's showing us how these things are being kind of channeled towards their different points in the base space. And the other perspective is to say that, well, we vary the thing in the base space, and as we do so, this kind of set or fiber above that changes. And so the basic idea of fibrations that we're going to look at today involves this concept, but also generalizations of it. So we can ask things like, what happens when, rather than this thing at the bottom here being a set, maybe it's actually going to be a category. So perhaps these are objects in a category, and maybe there's some arrows in this category. So in this case, where B is a category, so in this case, we might again have that there's a sort of set, which is the fiber above B1, and there's a set, which is the fiber above B2. But also this arrow F here in the base category will give us a function, which allows us to map things in one fiber to things in the other fiber. And so this is the basic idea. Actually, there's two different variants of this. This is the case with what we call opfiberations, and there's also something called fibrations, where it turns out that these functions go backwards. We're going to encounter this later, but this is the basic idea. So the simplest case is where this kind of function between these fibers goes in the same direction as the arrow that induces it. And this is an example of what's called a discrete opfibration. But we can get more elaborate than this, because it could be that actually these fibers above these objects here are not just sets. Maybe these fibers themselves are actually categories. So instead of having a sort of indexed family of sets, now we have a sort of indexed family of categories, or what's called an indexed category. And so this is a more elaborate scenario, which is called an opfibration. And then a fibration is the same kind of idea, but where the kind of functors induced by the arrows of the base category end up going in the opposite direction. And so these are the kind of ideas that we're going to come across. Now, it's a very, very quick introduction to what's going on, and I'm going to build up much more gradually, and you can see what's going on. Incidentally, I started with this kind of simple example where I just had everything was sets, and you can ask, is this the simplest kind of fibration? And there's actually something a bit simpler, which is that what if all of these sets are either empty or hold a single element? So we can have a situation like this. And if you think about it, what this is really describing here, like if we turn it into a function, so we say, okay, this is our total space, and we have a map like this. This is our projection P. Well, what this is really giving us is a subset, right? So when every fiber has at most one element, our fibration is just going to be sort of selecting a subset. And so in a sense, that's the kind of simplest thing that we find. So most of this video is about fibrations, but if you stick with it all the way to the end, there's a nice little bonus, which is that we're going to apply these ideas to talk about lenses. Now, lenses are used a lot in programming and computer science to handle these kind of situations where we have two-way flows of information. And it turns out that these ideas about fibrations we're going to cover today are pretty adjacent to a really powerful approach to think about all sorts of lenses and generalizations. And these kind of things have applications to the study of stuff like open dynamical systems and things like that. So very close to the end, I'm briefly going to mention how some of these kind of fibrational ideas can be used to understand some kind of very general perspective on lenses. All right then, so let's start talking about fibrations with a really simple example. So we're going to think about dynamical systems. So what we're going to do is we're going to think about some functor that goes from some category into set. Now, I'm going to pick this category here. I could really pick any category for the purposes of this discussion, but I like dynamical systems, so I'm going to pick this category here. So what's this category here then? Well, it has one object, which we'll just call dot, and that has an identity arrow, of course. It also has this arrow here, which we call sigma 1. So that's just an arrow from dot to dot. And if we compose sigma 1 with itself, we get sigma 2. And if we compose sigma 1 with sigma 2, we get sigma 3. And if we compose sigma 1 with sigma 3, we get sigma 4, and so on. So basically, you can think of this as just a sort of free monoid with one generator, which is sigma 1. So it's basically just this simple idea where we have a category of one object, which has an identity arrow, and this arrow sigma 1, and all of the sort of iterates of sigma 1. And what we're going to think about is a functor f from this category to set. And this is basically going to give us a dynamical system. The way you can think of this is that this functor f is going to send this object dot here to a set, and it's going to send sigma 1 to an update function, a function from that set to itself. And then sigma 2 is going to get sent to the function we get by applying the update twice, and so on. So this is the basic idea, and let's just dive into an example. So we could consider this case here. So here's our category B. I'm just drawing it in a bit of a different way. I'm only representing sigma 1 since what's going to happen to that really defines everything about this functor. And I'm drawing this dot twice just because it looks nicer. And so let's suppose that our functor then is going to send dot to this set of three elements, 1, 2, and 3, and it's going to send sigma 1 to this function here shown in blue. So this is our sort of update function. And so what this information really means is pretty easy to convey with a picture like this. Okay, so what we're really saying here is that we have a sort of dynamical system. The set of states is this set with members 1, 2, and 3. And then our update function, f of sigma 1, is going to send state 1 to state 2, state 2 to state 3, and state 3 to state 2. That's pretty much all there is to it. And it's pretty clear why this is called a dynamical system. So I've spoken about this idea a few times before, but you might be wondering, well, what does this have to do with fibrations? And the answer is really kind of hidden in plain sight, because in a sense, you're already sort of looking at a very simple example of one of these opfiberations, which is this sort of picture here this sort of state transition graph that I'm drawing at the bottom. But let me explain this a bit more carefully. So there's an idea that we've encountered before, particularly in the video on representable functors, and it's this idea of a category of elements. And so that's the thing I want to talk about next. So what is the category of elements of F? Well, it sort of looks like this picture here. A way that we can get it is by taking a look at this picture here of our functor, and then we're going to sort of rub out these bubbles, and we're going to consider these sort of blue threads here to become arrows. So let's call each of them sigma 1 because they're showing what happens when we do one update. And there's a bit of bookkeeping here. We better record the sort of object that these things are associated with in the base category. Well, there's only one object, so we've got to put a sort of dot on here. And what we have here is our category of elements, basically. And so, like, we really have multiple copies of the same object, so we don't need to draw it like that. We could simply draw the situation like this. We have 3 objects, dot 1, dot 2, and dot 3, and then each of these arrows here is showing us what happens when we do an update. If this doesn't make much sense, don't worry, we're going to see other examples of the category of elements and get at this idea more gradually. But the basic idea is that these kind of arrows here are showing what happens to the different elements when we update them by applying our functor to one of the arrows in the base category. So we'll call each of these arrows sigma 1 because they're showing what happens to our elements when we do one update. Now, as usual with dynamical systems, when we think about them category theoretically, there are more arrows that are going to be there. There'll be sigma 2 that illustrates what happens when we do 2 updates and so on, but we won't bother drawing those because they don't really give us any new information. They just sort of get in the way. So basically you can think of this picture here as this picture here is a sort of drawing of the category of elements of our functor F. And also this is going to come with this kind of projection functor here, which is basically just going to fold all of this stuff back down onto the base category. So it's going to send each of these arrows to sigma 1. And so what we have here is this projection functor P, which goes from our category of elements back to the base category. And this is the kind of structure that we're going to be mostly interested in. Now, let me talk through a more precise description of the category of elements. And so here it is. If we have a general functor F from a category B to set, then we're going to have this category of elements, which I'll write as EL of F. If I wanted to say what this is quickly, I would say that it is the slice category, star slice F. And if you don't know what that is, don't worry, because I'll go over a recap of comma categories and so on quite shortly. But here's an explicit description of this category of elements. So it has objects that correspond to pairs of an object B from this base category scripty B, and an element X of F of B. So remember, F of B is going to be a set because F is sending these objects of B to these sets F of B. So that's what the objects of the category of elements look like. What about the arrows? Well, an arrow from B comma X to B dash comma X dash is just going to be an arrow G in the base category, which has the feature that if we get this arrow G in the base category and we apply F to it so it becomes a function, then that's going to send X to X dash. And so the sort of picture to have in mind is something like this. we've got our base category B. There's going to be some objects in it like B and B dash, and probably some arrows like G. And then we have this functor F, which goes from that to set. And so this B here is going to get sent to some set F of B. B dash is going to get sent to some set F of B dash. And so we're going to have some sort of elements in here, like we might have an element X in the set F of B. And we might have some element X dash in F of B dash. And then also this functor F is going to send this arrow G to some sort of function F of G, which goes from F of B to F of B dash. And then the idea to get the category of elements is we sort of rub out these bubbles, and then we're going to index these things properly. So we recall that this X here is associated with B, and this X dash is associated with B dash. And then we're going to have an arrow from B comma X to B dash comma X dash, which is called G, precisely when this X dash here is the thing that we get by applying the sort of lifted functor on X. So basically these kind of arrows, in this elements category of F are indicating how different elements get converted to other elements under the sort of lifted versions of the morphisms in the base category. And there's also going to be this sort of projection functor here, P, which takes these things in the category of elements and it just sort of gives us the indexes for those things. And that's going to be our projection functor. And this is our sort of quintessential example of a discrete opfibration. Okay, so I think the easiest way to introduce these opfibrations is to show you simple examples. So let's suppose that we have some functor F from some category B into set. And I've picked this case where F really corresponds to a graph. So just for this example, suppose that this category B has these two objects here, E and V, and these two arrows here, S and T. And so when we apply this functor F, E is going to get sent to an edge set, V is going to get sent to a vertex set, S is going to get sent to this function which associates each edge with a source, and T is going to get sent to this function which associates each edge with the target. And so I've drawn an example graph F here at the bottom, and you can see that this functor F in this example is going to send the edge set to this set of two edges A and B, and this arrow S here gets sent to this function F of S, which is pointing every edge to its source vertex, and so on. So this is just the usual idea of a functor, which goes into set. And then what we're going to do is we're going to get the category of elements of this functor. And the simplest way to think of this, I reckon, is you look at this kind of picture here, which is sort of showing us how the functor works. And then we're just going to sort of change it a little bit. So we're going to rub out these bubbles. And we're going to remember where our objects came from by sort of indexing them. So we'll put an E on the front of these because these came from E. These get a V on the front. And then these arrows here that are sort of showing us how our functions work are going to become arrows in our category. The red ones we're going to label with an S because they were made by our source arrow. And the green ones we're going to label by a T. And so now we have this category. It has 4 objects, 1, 2, 3, 4. And it has these 4 arrows. 2 of them are called S, It's okay if we give them the same name because they have different sources and targets, so we're not going to get confused. And also we've got these two arrows called T, and we're going to have some identity arrows as well. So in total, we're going to have 4 identity arrows, 2 arrows called S, and 2 arrows called T, and we're going to have 4 objects. And this is our category of elements of our functor F. And we'll call this EL of F. And so that's the basic idea. And you can do an analogous thing when you have any functor from any category B into set. So basically the way I think of it is you can draw your functor F by drawing these sort of bubbles which show the sets that, you know, your objects of script B get sent to. Then you can draw these threads that show you how these functions work, you know, the functions you get by applying F to the arrows of script B. Well, then if you sort of rub out the bubbles and think of those threads as arrows, that's basically your category of elements. And the important thing for us today is that there's going to be a sort of projection functor we could call P. And it's just going to go like this. It basically just remembers the sort of index. So, you know, E comma A gets sent to E, E comma B gets sent to E because, you know, those two things are indexed by E. Of course, these green arrows up above get sent to the green arrow below, and the red arrows up above get sent to the red arrow below. So this is our functor P, and this is going to be a functor from our category of elements to our sort of base category, script B here. And this kind of functor P is what we call a discrete opfibration. And these are the kind of things we're going to start by studying because they're pretty simple examples of opfibrations. So what we're going to need to set this up is this idea of this interval category here. This is just this category that has one arrow between distinct objects together with identity arrows. So this is sort of, sometimes I call this category arrow. And so it's interesting then if we have some category D, we can form this category here. So this is the category of functors from I to D. And this is sometimes called the arrow category of D. Now this, it turns out, is going to be pretty important for us. It has lots of nice connections with fibrations that we're going to see later. What is this category explicitly? Well, it has objects which correspond to arrows. So this F is going to be an object in this arrow category, as is this F dash. And what's going to be a morphism from F to F dash? Well, that's just going to be a pair of arrows of D, U and V, which make this square commute here. So that's the nature of this arrow category. And there's something important about this arrow category. Most important for us is going to be that there's this functor called cod, and it turns this arrow category into a fish. No, it doesn't. It gives us the codomain of the arrows. So the way it works is it's going to send this object F here to Y, and it's going to send this object F dash here to Y dash, and it's going to send this arrow U comma V to V. So that's how cod works. And in a similar way, there's another functor which is called dom, and that gives us the domain of stuff. So it sends F to X, it sends this morphism to U, and it sends F dash to X dash. So it gives us the domain of everything. Another idea that comes up a lot in this video is comma categories. So I thought it's worth, again, quickly going through a definition of a comma category. So suppose that we have a couple of functors R and S, which both go into a category D. Well, then we can form the comma category R slice S, or R comma S. And this is a very useful idea for us For example, when R is this functor that just creates a singleton set and F is some other functor into set, well then in that case this comma category star slice F is actually our category of elements. So that's one reason comma categories are useful. But how do we get comma categories in general? Well, if we have these functors R and S, then this comma category here, well, its objects consist of triples of an object A of big A and an object B of big B and an arrow F from R of A to S of B. And then a morphism from one of these triples, A, B, F, to another of these triples, A dash, B dash, F dash, is just going to be an arrow M from A to A dash and an arrow N from B to B dash, which have the property that they make this kind of square commute when we do R on the M and when we do S on the N. So that's a sort of quick introduction to comma categories. Sometimes I might write the comma category like this, just be a bit more explicit about where these functors come from. So R slice S like that. Sometimes we might think about the case where we have that the first functor is an identity functor and the second functor is picking out some object D, and that kind of thing is sometimes written as scripty D slice little d, and that's sometimes called a slice category. And there's also the other idea kind of upside down, which would be like where it's the top functor that's picking out a single object and it's the bottom functor which is the identity. And that kind of thing is sometimes written as D slice scripty D, and that's sometimes called a co-slice category. Incidentally, this category here, identity of D slice identity D, is actually equivalent to the category of arrows of D itself. So you see already that this concept is very, very rich, this concept of comma categories. Okay, so this category of elements interacts with lots of other mathematical structures, and in my opinion, it has a very kind of visual flavor. And so it's very interesting to see this category of elements doing its thing, because it usually gives one a nice kind of visual perspective on different things in mathematics. So here's another way to think of the category of elements. There's actually a few different sort of equivalent ways that one can define it. And one of them is as this sort of pullback square. So this is a pullback in cat. So remember, cat has objects corresponding to categories and arrows corresponding to functors. And so we can draw this kind of diagram here that I'll explain momentarily, and then we can compute the pullback of it. Now, the way that you compute pullbacks in cat is pretty much very similar to how you compute them in set. You remember when you compute a pullback in set, you're taking the set of pairs of an element from this set and an element from this set, which have the property that if we apply F on the first element, then we get the same result as if we apply this functor on the second element. And so if you apply that same kind of thinking to the objects of these categories, then you get the set of objects of this category of elements. And you can see that, you know, an object in this category of elements is just going to consist of a B and an X, which is in F of B. And also you can apply exactly the same kind of reasoning for the arrows. If you want to get the arrows of this thing, you look at the sets of pairs of an arrow of this and an arrow of this, which have the feature that if we do this functor on the arrow from here, we get the same result as if we do this functor on the arrow from here. So that's a sort of 1 minute recap of how we get pullbacks in cat, but like, what are we actually doing a pullback of? Well, this is just our functor f that we're sort of making our category of elements from. This thing here is what we could call the category of pointed sets. So this has objects which correspond to sets with distinguished elements, and then the maps are just these functions that preserve these distinguished elements. So there's various interesting sort of equivalent ways to think of this category of pointed sets. Another way you can think of it is if you get the maybe monad on set and you take the Kleisli category of that turns out to be equivalent to this category of pointed sets. You can also think of this as the category of sets and partial functions. That's again equivalent. But there's clearly going to be this sort of forgetful functor u here, which takes a pointed set and forgets the point. And it turns out that if we do this pullback, we get the category of elements. And it's kind of interesting because, like, there's some kind of, if you remember from topos theory, this idea that you'd have something like a truth value object, and you'd have something like true, and then you'd be pulling that back along f. You can see that there's something similar going on here with these categories of elements. So that's kind of interesting, but I won't go into that more now. Okay, so now I want to talk about something called discrete opfiberations. Now, these sound complicated. They sound kind of overly elaborate, right? It's not just a vibration. It's not even a discrete vibration. It's a discrete opfibration. So they sound kind of like something that, you know, is in the back attic of mathematics, but actually these discrete opfibrations are super important, and they're some of the kind of simplest structures that we can use to really understand what fibrations are all about. So what is a discrete opfibration? Well, it's a functor that has certain properties, and the basic idea is that it works like the projection functor from the category of elements. So the basic idea is that it's a sort of abstract definition that's designed to recover the thing that's happening when we take the category of elements of something. So the easiest way to understand what discrete opfibrations are is just to think about the category of elements. So we'll come back to this proper definition momentarily, but so okay, to introduce this idea of discrete opfibrations, let's think about the category of elements, because really that's the main place where we get these examples of these discrete opfibrations. In a sense, it's the only place. So suppose that we have a functor f from beta set, and we want to think about the category of elements of f, and let's call that E. Now, what are the objects in this category of elements? Well, they're going to be things like this: a pair of an object of our base category script B and an element x of f of b. So that's what the objects of this category of elements look like. Now, let's think about a particular question. Suppose we have an arrow G in this base category here. And what we want to know is, are there going to be some arrows, like let's call an arrow phi, within this category of elements here, which are going to come out of b comma x, and they're going to be such that they're going to get sent to G under this projection functor. Okay, so this is the basic setup. We start off with an object in our category of elements, let's call it E. Well, we know that we can write it as B comma X. And so we know that this projection functor is going to send it to an object B. We could equivalently call this P of E. And then what we're going to do is we're going to take a general arrow G that comes out of P of E, and we're going to ask, what are the arrows that get sent to G under this projection functor? And the key thing to understand here is that if we say, oh, well, phi is such an arrow, well, of course, phi is going to have to get sent to some target E dash. Actually, we can figure out what E dash has to be, right? Well, at least we know that E dash is going to get sent on top of B dash. So we know that E dash is actually going to have the form B dash comma X dash for some element X dash of F of B dash. But we can do better. Why can we do better? Well, actually, if you think about the way the category of elements works, the arrows in the category of elements are actually sort of called the same things as the arrows in the category B. And in fact, this projection functor kind of preserves those names. So in a sense, we could say that phi is going to be G. And also we know that X dash here is going to have to be a very particular thing. It's going to have to be F of G of X. And so what we find out, and this is the sort of big revelation, is that actually there's only a unique arrow. So there's a unique arrow phi that has this feature that it's going to get sent on top of G. So let me just reiterate. What we've basically argued here is that if we pick an object E in our category of elements, and then we pick an arrow G that comes out of P of E in our base category, then there's going to be a unique arrow phi, which is in our category of elements, which has the feature that P sends it to that G. And basically the reason for this is because the arrows coming out of stuff in the category of elements are sort of defined by their source object and what they get sent to in the base category, because then to find out the target object, we're just sort of basically like applying a map to an element. Now, all of this might sound rather abstract, and it kind of is, but roll with it, because it really gives us a very nice bridge between two different things. So basically what I've just described is exactly the definition of a discrete opfibration. So what we basically do now is we say, well, okay, let's just make this all a bit more abstract. So what we basically say is, well, we're not really caring now to say that this category E is the category of elements. Let's just suppose that we have some object E. And now what we want to say is that this category E comes with a functor P that goes to a category B. And it has the feature that if we take some arrow G from P of E to some other thing, let's say B dash, well, then there's going to exist a unique arrow phi. So something like this, which has the feature that P of phi equals G. Okay, and that's it. It turns out that if we look at things abstractly like that, that's kind of enough to specify that we're dealing with a category of elements. So let's be a bit more precise about this now. So I was just basically trying to motivate this definition, which is our definition of a discrete opfibration. So to be more precise then, if we have a category E and a category B and a functor P. We say P is a discrete opfibration if and only if for every object E within our category script E, and for every arrow G from P of E to some object B dash within our base category B, there's going to exist a unique arrow phi in E, which has the feature that this functor P sends phi to G. And what's the point of this definition? Well, the point of this definition really is that when this holds, it turns out that basically we can find a functor f from B to set, which is such that we're going to have that E is equivalent to the category of elements of F. And this P is going to turn out to look like the projection functor that comes from that. That's at least the kind of rough way that I usually think about what discrete opfibrations are all about. But, you know, this is the formal definition. And the point somehow is to kind of describe what's happening with the category of elements, but a little bit more abstractly. Now, we can be more precise about how discrete opfibrations relate to categories of elements with this kind of result here. So what we can do then is we can actually define a category of discrete opfibrations. And so again, I'd encourage you to think of a discrete opfibration as like a category of elements with a projection functor. At least that's how I like to think of them. But, you know, we can define them we can also think of a discrete opfibration just as a functor that satisfies that rather abstract definition that I just went through. And so that means that a discrete opfibration is basically a kind of functor, something that goes from some category E to some category B. And, you know, cat has arrows as functors. And if we consider cat slice B, well, an object of cat slice B will be a functor that goes into a category B. So we could say that this functor P here is an object of cat slice B. And so actually what we can do is we can define the category of discrete opfibrations of B. It has objects as discrete opfibrations. So this P here would be an object of this category of discrete opfibrations. So in particular, we can define this category D opfib, and that's the category of discrete opfibrations of B, and it's basically just the full subcategory of cat slice B on the objects that correspond to these discrete opfibrations. So like this would be an object of cat slice B. So like this would be an object in this category. Let's say this is another object. And then what would be an arrow from this first object to this second object in this category here? Well, it would just be a functor, let's say H, which makes this triangle commute. So P dash after H equals P, that kind of thing. So that's what this category of discrete opfibrations of B looks like. Okay, so now we've got all this stuff in place, we can talk about a very, very interesting result. And what this result basically says is that, like, if you have an object B and you're interested in the category of functors from B to set, well, we've been interested in this kind of thing a lot, right? Like, we're interested in stuff like dynamical systems and graphs and simplicial sets. And we can think of each of those in terms of some particular functor category. Well, it turns out then that that kind of category, which has, objects as functors and arrows as natural transformations, that is actually going to be equivalent to this category of discrete opfibration of B. So this is very, very cool. What it's basically saying is that, we already know that if we take a functor F, so an object in this category, well then we can consider the category of elements of F, and that's going to come with this projection functor into B, and this is going to be a discrete opfibration. So we know that we can sort of send these functors F over here to these discrete opfibrations. Actually, we can do this by doing this kind of elements construction. It turns out that that's actually a functor from this category here to this category here. But it's very interesting that this is actually an equivalence of categories, because it's kind of saying that if we're interested in studying these kind of things, which are sometimes called co-presheaves, these functors from some category beta set, well, it turns out that basically the category of co-presheaves of B is equivalent to the category of discrete opfibrations of B. And so, looking at things from the perspective of the elements category is sort of equivalent. And that's very cool because it gives you a different perspective on things, a perspective where we have more categories and where we're sort of, it's always useful when you have stuff like natural transformations and you're able to look at them in a different way, and it gives you a different sort of perspective on things. And this kind of bridge does that for us too. So this is the result spelled out a bit more carefully. What we're saying is that if we have this category of functors from beta set, there's this functor from that to this category of discrete opfibrations. So, how does this functor work? Well, it's going to send an object F of B comma set to the category of elements of that, which we could call EL of F. I mean, that's really going to come with this projection functor as well. I kind of often prefer to write it as star slice F. But yeah, that's basically what this functor L is going to send F to. What does this do to the arrows in B comma set? So an arrow in B comma set is going to be a natural transformation alpha from F to F dash, and that's going to get sent to this functor here, L of alpha, and that's going to be a functor from the category of elements of F to the category of elements of F dash. And basically the way it works is kind of if you just think about it for a while and think about what, there's pretty much only one kind of canonical choice that you'd want to set up, and it's basically, well, if we have an object of this category of elements here, that's going to be an element X of F of B. And if we just do the beef component of alpha after that, that gives us an element of F dash of B. And so this is showing us how L of alpha works on objects. And the way it works on arrows is basically it keeps the names the same, basically. So this is our sort of functor, which allows us to convert from these co-presheaves to these discrete opfibrations. And this is an equivalence of categories. So this is pretty useful because it kind of allows us to take a sort of elements-centric or discrete opfibration-centric view to lots of things that we've been doing with these categories of functors. And I'd argue that this is actually a pretty natural way to think about a lot of things that we've seen before. So it may seem kind of abstract and stuff, but think about the category of dynamical systems, for example. So, you know, we have this sort of free monoid with one generator. We have the category of functors from this into set, and each of those kind of functors corresponds to a dynamical system. So, for example, this dynamical system here is like that would be like where we do a functor from this into set, and this functor is going to send this object here into this sort of 3-element set, and this arrow here is going to become this update function that sends this left dot to this middle dot to this right dot, and this right dot to this middle dot. But the thing is, like, look at how. Okay, so I should write it like this, otherwise it's going to get confusing. So this is set, and what we're really doing is we're sending this object here to this set here, and this arrow here is going to become this update function. The thing is, though, take a look at these pictures. Do these look like sets with functions attached to them? I'd say they look more like categories, right? Like, what we're really sort of picturing here are objects and arrows which are showing how these sort of objects are getting updated. And so in a sense, I'd say that what we draw normally when we think about dynamical systems are basically these sorts of categories of elements of these functors. And so in a sense, we're already picturing these discrete opfibrations. I mean, really, discrete opfibrations are going to be things like the category of elements of F, which kind of looks like this. I mean, yeah, there's more information in the category of elements in the sense that we'd be drawing extra arrows which show what happens when we do 2 updates, 3 updates, and so on. But, like, you know, we just don't have to depict those. If we just show these arrows that show what happens when we do 1 update, this is pretty much like a category of elements. And yeah, okay, like, there's also this projection functor here, which would be folding us back onto our free monoid, which we're sort of not drawing, but, you know, that's okay. Basically, I'd say that it's quite natural to think of a lot of these functors that go from some category B to set in terms of these discrete opfibrations. So yeah, I mean, actually, you know, this goes even further. So we could ask, like, what's a morphism from this dynamical system here to this dynamical system here? And, you know, the usual answer is, well, it's just going to be like a natural transformation alpha from F to G. But, you know, if we go from this category of co-presheaves to the category of discrete opfibrations, we get a kind of different perspective, which is that really we can think of this alpha as a sort of functor which goes from this category here to this category here, and it sort of works so that this kind of triangle commutes here. And, you know, again, I kind of think this makes quite a lot of sense. So in a sense, we could say that what we have here, we could think of as something happening in cat, where we have a kind of commuting triangle like this. So yeah, this is the sort of idea I'm trying to get across here. It's that this way of converting from functors from B to set to discrete opfibrations is important. And like, it's useful to sort of meditate on what this does to special kind of functors. So, for example, a special kind of functor from B to set is going to be a Hom functor. So what happens to a Hom functor when we do this category of elements thing? Well, we get the category of elements of the Hom functor, of course, and that comes with a projection. But really this, it turns out, is equivalent to a little b slice scripty b. And that turns out to be a pretty interesting sort of fact. Like, another thing which is kind of interesting to think about is the Yoneda lemma. So really, the Yoneda lemma is kind of something that has to do with this category here of co-presheaves. But, using this kind of equivalence, we can also now think of the Yoneda lemma as something that has to do with discrete opfibrations of B. So I'm not going to go through this in great detail. You can check out the appendix, I think it is, of Fosco's book, Coend Calculus, if you want to see more about this. But the basic idea is like this. The Yoneda lemma basically says that these kind of natural transformations, alpha, from like a Hom functor into f, are in a sort of natural correspondence with the elements of f of b. And, we know how this works. But now we can say, well, okay, this is like an arrow in our category of co-presheaves. What does it look like if we translate it in terms of discrete opfibrations? And well, we know that this Hom functor here is going to get sent to this category of elements, and that ends up looking like little b slice scripty b. So this ends up getting sent to this, and then alpha gets sent to L of alpha, and f gets sent to its category of elements. And so what we're really saying is that this kind of natural transformation alpha corresponds to this kind of functor L of alpha, which is like a morphism of discrete opfibrations. And also, like, if you think about it, little b slice scripty b is going to have a special object, which is going to be this object, which is the identity arrow of little b. And like that's going to get sent by L of alpha to a particular object in the category of elements, and it's actually going to be this one here, which is going to be basically the element which sort of corresponds to alpha. And it turns out that this element here is really the special element of f of b, which corresponds to alpha under the Yoneda lemma. So this gives you a sort of different view of the Yoneda lemma in terms of discrete opfibrations. Another thing I sort of can't resist mentioning, but I'll try and mention it as quickly as possible because there's so much to go through. But this other thing was really the focus of my video on representable functors. And it's this very beautiful result, which says that if we have a functor u from a category A to set, then we're going to have a sort of representation of that, which means that we'll have a special object A star and a natural isomorphism phi from this Hom functor here, which, we could also write as like Hom subscript A star comma blank. Well, we'll have a natural isomorphism phi from this Hom functor to u if and only if the sort of element corresponding to phi is going to give us an initial object in the category of elements of u. And look at my video on representable functors if you want to see this unpacked in more detail. But it's like a really awesome result because, for example, this lets you understand like loads of stuff about adjoint functors. So in particular, suppose that we have that L is the left adjoint of R. So that means we have this kind of natural isomorphism here. So we have this phi here, which is a natural isomorphism from this functor to this functor. Well, this functor on the right, this is a functor from A to set. We could call it U. And we want to think about this as a representable functor. So let's call this thing here A star. like this. And then this equation here becomes this. So phi is a natural isomorphism, basically exhibiting u as a representable functor in terms of this object A star and this natural isomorphism phi. And then the previous result says that this kind of element that sort of corresponds with phi under the Yoneda lemma, we could call it phi hat or phi of A star of the identity. Well, this is going to be an initial object of the category of elements of U, and we can write it like this. We could write it like this. We could write it like this. We have these different forms for the category of elements of U. And what is this that we've just figured out? Well, it turns out it's actually just the unit of our adjunction. So basically what this is telling us is if you have the kind of natural isomorphism in terms of these Hom sets that's describing this adjunction, you can use it to get the unit of your adjunction, and you can go the other way as well. So this is a very cool result. So I want to move on now to sort of punch things up and go to a higher perspective and look at a more sort of elaborate fibration, which is not discrete anymore. Just one thing before we move up a level is this other very interesting result. So you may recall that if you're working with the category of sets, you can always sort of factorize a function. So let's look at a function from 1, 2, 3 to A, B, C. Let's do this one here. So we'll send these elements like this. Now it turns out that we can factorize this. So we can factorize it into sort of two steps. So firstly, we're going to do this epimorphism here. And then we're going to do this monomorphism here. So in this way, we can factorize any function f into an epimorphism followed by a monomorphism. And so that's something that we can do in the category set. So we could ask, what about cat? Can we factorize arrows in cat? Is there a sort of special way that we can always break arrows in cat into two different forms? And it turns out that there is. And so we have this very interesting result, and it's called the sort of comprehensive factorization of a functor. So suppose we have a general functor f from a category A to a category B. Well, it turns out that we can always write f as some functor w followed by a projection from a category of elements. So in other words, we can always factorize any functor through a discrete opfibration. And how this works is sort of quite elaborate. And there's quite some interesting details behind this construction. The basic idea is that if you have a functor f, then you can find a functor k and a functor w such that you can do w and it goes to the elements category of k, and then you can do the projection functor from that back into b, and that'll give you your functor back. So I've added a video, an unlisted video. So if you have a look at the description of this video, I've put a link to an unlisted video where I talk about this result and how we actually do this construction. It's kind of involved, so I thought I'd leave it out of the main video. But it's a very interesting kind of construction that involves interactions between can extensions and different perspectives on comma categories and things. It's a very interesting construction that I got interested in through this paper on vibrational linguistics. So it turns out that there's a way to think about like linguistics in terms of vibrations, and then this kind of construction here turns out to be sort of related to how people can understand each other when they use language. At least that's what the authors of the vibrational linguistics papers propose. Okay, so we've got some understanding of these discrete opfiberations. What we want to do now is to sort of level up and think about more general kinds of opfiberations. So we're going to now look at one of the most interesting constructions in category theory, which is called the Grothendieck construction. And it's a really beautiful idea, which basically allows us to attach together lots of structures in a very kind of coherent way, and really lets us organize all sorts of knowledge. So I think the easiest way is if I just introduce this idea directly, and then I'll talk more about some sort of motivations and ideas behind it later. So we want to talk about this Grothendieck construction, and the sort of main building block for this is going to be a functor that goes into cat. So now we're going to think of f as a functor from a category B into cat. So in a sense, the Grothendieck construction allows us to organize the kind of data behind this functor into a single coherent sort of structure, in an analogous way to how the category of elements allows us to represent a co-presheaf. So in a similar way, the Grothendieck construction gives us a category that represents a functor like this f. So in a way, the most important thing is, what does a functor f from a category B to cat look like? And the basic idea is that we're going to have this category B, so it might have objects like little b and little b dash, and it might have arrows like g, and so this would be a part of our base category B. And then the idea is that this functor is going to send this little b to some category. So this would be some category, let's say this is f of b, and then also b dash is going to get sent to some category. So maybe it looks like this. This would be f of b dash, like so. And also this functor f is going to send the arrows of b. For example, this arrow g is going to get sent to a functor. So that will be a functor from f of b to f of b dash. So that would be big F of little g. That would be a functor. And so we sometimes call things like f of b or f of b dash fiber categories. So we might call f of b dash the fiber category over b dash. And the idea basically behind the Grothendieck construction is that we're going to sort of collect together all of this data here about these categories, these fiber categories above these objects of B and these functors. And in a very rough sense, we're going to sort of rub out these bubbles and think of what we've got remaining as a kind of category. And we can call this category E, keeping our naming convention, or we could call it the Grothendieck construction of this functor F. And it's pretty analogous to the construction for the category of elements. The main difference is that the sort of fibers above the objects of B are not just sets, they're now categories. And of course, this thing comes with a kind of projection functor P, which goes into our category B, and that is what we call a opfibration. So that's a sort of 1 minute introduction to Grothendieck constructions. Now let's go through the details more gradually. So yeah, the idea is that we start with a functor f from a category B into cat, and we can really think of such a thing as a sort of indexed category, if we like. So think about a sort of category that varies as we change the object of B, and the arrows of B give us functors between these different fiber categories. So this is the data that we start with, and then the Grothendieck construction is where we get that kind of thing and we sort of glue it all together into a big category. So the setup is very similar to the way the category of elements is. It basically is the same as the category of elements, except that we might have some sort of arrows within these fibers, and that leads to some more elaborate structure. So the objects of this Grothendieck construction, which is a category, so gr of f is a category called the Grothendieck construction, and it has objects which correspond to pairs of an object in the base category B and an object X in the fiber category above B. So remember, f of B here is a category, and so an object in the Grothendieck construction of X consists of an object in the base category and an object in the fiber category above that object. So for example, if we have an object B in the base category and an object X in f of B, then together that pair of B and X is going to be an object in this Grothendieck construction of f. And so that's what the objects of the Grothendieck construction look like. What about the arrows? So an arrow from B comma X to B dash comma X dash consists of a pair. And the pair is that we have, and consists of a pair. And this pair is like, well, we have an arrow G, which goes from B to B dash in the base. And then we have an arrow H, which goes from where X gets sent by the kind of substitution functor, f of G, to X dash. So an arrow in the Grothendieck construction looks like a pair of arrows like this. The easiest way is for me just to show you what this looks like in a picture. So here's a kind of picture of it. So what we're trying to picture here, just focus on this part of the picture for now on the left. And what we're trying to picture here is what an arrow from B comma X to B dash comma X dash looks like in the in this Grothendieck construction. So we'll call this arrow G comma H, and what it consists of is an arrow G in the base category that goes from B to B dash, together with this arrow H, and this arrow H goes from f of G of X. So remember that f of G is a functor, so it's going to send X to this object fg of X, and then we want H to be an arrow from that destination to X dash. So the way that I think about an arrow like this, actually I like to think about Star Trek for this. So I imagine that the crew of Star Trek are trying to get inside some alien building, which then they can't transport into. So the first thing they need to do is to teleport from the ship to outside of the building. And so they have this kind of pad that controls the transporter, and they have to put in the current coordinates and the coordinates just outside of the building. And this kind of arrow here would be, how you can relate the two things inside a program that you put into the transporter mechanism in the Starship. And then when you sort of apply this functor here, this allows them to transport from their current location to the location in the planet. So this functor F here is sort of translating the information on the transporter to actual movement from the current location on the Starship to the location on the planet. But then once they've transported down onto the planet, they're still outside of the location that they have to get to. So they have to do this arrow H, which is like moving on foot. So it's the kind of idea like once you've moved somewhere near your destination, you have to do a kind of secondary stage of the journey where you kind of have to, walk the last bit. This kind of, drive near to the location, then walk the last bit. So that's what an arrow looks like in this Grothendieck construction. To be a bit more precise, it just consists of an arrow G in the base category paired with an arrow H from f of g of x to x dash. And so this is the basic idea. And hopefully you can see that the category of elements is really like a special case of the Grothendieck construction. So in particular, before, what we were dealing with were these functors which went from a category B to set, and then if we just sort of did an inclusion from set into cat, which we can do because like every set can be thought of as a discrete category. So there's this kind of inclusion functor from set into cat, which just sends every set to the corresponding category that has that same set of objects, but only identity arrows. Well, if we compose these and then we cook up the Grothendieck construction of this kind of functor, so if we basically consider the Grothendieck construction of I after F in this case, that's going to look like the elements category of F. This is the basic idea. But anyway, going back to talking about the Grothendieck construction more directly, I've now told you what the objects are and what the arrows are. Of course, I still need to tell you the other two things that you need to know, which are about identity arrows and composition. So what about identity arrows? So if we have an object in the Grothendieck construction, say b comma x, then how can we find an identity arrow of it? Well, we want an arrow from b comma x to b comma x, and we know that that's going to be a pair, g comma h. And so since we want an identity arrow, let's pick g here to be this identity arrow of b. And then we know that we want H to have this kind of form. But, we know that this G is an identity arrow, so this is just going to be X here. And so why don't we just pick H to be the identity of X? So yes, this is what the identity arrows of the Grothendieck construction look like. They're just pairs of identity arrows. The way that composition works is a bit more interesting. So I'm trying to illustrate how composition works with this picture here. So let's look at this a bit more explicitly. So suppose that we have a couple of arrows in this Grothendieck construction, so G comma H and G dash comma H dash, and we want to compose them. So let's say that this is their composition. So the composition, again, is going to be a pair of arrows. The first arrow, we just want something that goes from B to B dash dash in the base category. And of course, we're going to take G dash after G. The second thing is a bit more interesting. So we also want to get the sort of second entry of this arrow, which is this composition here. And what we want this to do is we want it to go from G dash after G, lifted by F, applied to X. We want it to go from that to X dash dash. That's the form that we want H bar to take. And the question is really like, how do we cook up this H bar? And the answer is basically shown in this picture here. So what we do, firstly, we know that we have this arrow G comma H. So that consists of this data and this data here. Now, if we do F of G dash on this arrow H, that'll give us this arrow here. And if we compose that with this arrow H dash, which, we get from this sort of second leg here, then indeed that composition has the appropriate form. And that's what we define H bar to be. So that's how composition works in this Grothendieck construction. So I've now given you the full definition. It's a lot, like I think, when you first see it, but I encourage you to look at some examples, right? Like it's quite easy to think of functors that go from some category B into cat, and then you can start doing Grothendieck constructions of them. And if you do a few of these examples, like, you'll start really getting into it, I think, because it really is a very beautiful kind of construction where you're attaching together all sorts of structure. And yes, it's very interesting. So the other important thing to say about the Grothendieck construction for us today is that it comes with a projection functor. And that's going to be a functor which goes from this Grothendieck construction to the base category. And it kind of works in a similar way to the case with the category of elements. So in particular, if we have an object in this Grothendieck construction, that's going to be like a pair, B comma X. And P is going to send this to the object B. And if we have an arrow in the Grothendieck construction, say G comma H, which goes to B dash comma X dash, well, that's going to get sent, as you probably guess, to this arrow G from B to B dash. And that's it. This is probably one of the, and that's it. This is one of the big ideas in category theory, this idea of a Grothendieck construction. Okay then, so now we know what Grothendieck constructions are. Let's take a look at an example of one. So this is a nice example that we're going to look at again later. And basically what's going on here is that we've got a particular functor from our category B into cat. And we've got this, and this is our functor F. So here, B can be any category that we like. And we're going to make a very particular functor from B into cat. And basically it involves forming these slice categories. So what we want to do is we want to send the objects of B to categories. In particular, we want to send little b to this category here, which is scripty B, slice B. So we're basically sending an object B to the category we get by slicing using that object little b. And then if we have an arrow G, then that's going to get sent by F to this functor here. And the way this functor works, which I'm calling this functor B slice G, the way it works is that if we have an object in this slice category here, that'll be like an arrow, say from some A to B, well then this functor is going to send that to this arrow G after E. And it basically leaves the morphisms in these slice categories having the same name. So that's how this functor works. So basically, this is going to be f of b as the slice category, and this functor here is going to be f of g. And it basically works by taking the objects in this slice category, which are really arrows into little b, and then post-composing those arrows with g to get objects in the slice category b slice b dash. So that's how this functor works. And then the interesting thing is that when we do the Grothendieck construction on this functor f, we get something pretty interesting. We actually end up getting the arrow category of b. And I'll leave it to you to work out the details of that. It's a great exercise that will help you to understand a lot about Grothendieck constructions. And of course, this Grothendieck construction comes with its projection functor back to the base category. And it turns out that that ends up being the sort of codomain functor that we talked about before, that sort of sends these arrows, these objects of I, b to their codomains. And so this is the sort of opfibration which we get. It's the functor that sends our arrow category of b to b itself by getting codomains. And so the sort of other way you can think about this is that, like, yeah, we have this functor from b to cat, and it's kind of like an indexed category. It's like we're varying the object of b and we're getting this slice category. But if we sort of do the Grothendieck construction of f, we're really sticking all these slice categories together, and that's going to give us this arrow category, and that's going to be sort of like our total category, our total space. And then the kind of projection functor that goes back into b is really sending every arrow to its codomain. And if we think about this situation here, like if we picked a particular object b, and then we looked at the stuff that get sent on top of that b by this codomain functor, that would look like this kind of fiber category above b, which is the slice category, right? Because this has objects that consist of arrows that go into b. They're the objects which of this category of arrows which have codomain b. So this is a really nice example to study and get a lot of intuition about how Grothendieck constructions work. Now, what we're going to do next is sort of rocket boost a bit and get a bit abstract, because suddenly loads of ideas come at the same time. So this is a bit like, I think this is a bit the issue with learning Fibrations. It's the ideas are almost too good. Like so many things come at the same time that it can get a bit much. So if you just stick with it, after we've gone through these main ideas, we're going to slow down and look at some examples, and then things will get more clear. But let me sort of get a sort of higher level perspective. So one thing that we were doing earlier on was we were noting that we have this sort of equivalence between co-presheaves of B and the discrete opfiberations of B. And now what we're doing is we're sort of generalizing everything. So rather than looking at these functors here from B to set, we could really think of them in a sense as functors from B to cat that send the objects of B to discrete categories, if we like. That, working with discrete categories is kind of like working in set, right? So basically I'm saying that this category here, it can be included in the category of functors from B to cat, right? This is sort of more general thing. And if we have this, then it turns out that we have something that this is equivalent to, and this, okay, this is not really true, but just to say approximately, this is sort of equivalent to the category of what we call opfiberations of B. Now, there's a bit of a caveat here that I'll get into, but basically the idea here is that we're generalizing this structure here on the left, and we're going to do a sort of corresponding generalization of our notion of discrete opfiberations, and this is going to give us the idea of something called an opfibration. And the basic idea is that this Grothendieck construction, okay, so the idea basically is that the elements category is to discrete opfiberations as the Grothendieck construction is to opfiberations. So we're sort of generalizing everything. And so this is really the big idea is this. The big idea is this little picture here. So basically, what we can do is if we have a functor from B into cat, we can do a Grothendieck construction on it. And we get this, we get this category called, so if we have an F here, we get this category called GR of F, and it comes with this projection functor into B. And it turns out that this is always going to be something called an opfibration. And basically we have a sort of equivalence where these kind of opfiberations end up corresponding to these functors from B to cat. Now here there's a bit of a caveat that I kind of don't really want to get into at this point, because I think it's a bit of a distraction. But it turns out that actually to get this equivalence, we want to have something a bit more general than just a functor from B to cat. It turns out that there's something called a pseudo functor, which is sort of like a generalization of a functor. So when you have a functor that goes into a 2 category, cat, we can really think of cat as a 2 category, right? Because it has these 2 cells that are natural transformations. Well, when you have like a functor that goes into a 2 category, you can kind of generalize that notion to get something called a pseudo functor. And the idea with a pseudo functor, like very roughly, is that you're sort of generalizing things. So ordinarily with a functor, it has to preserve composition exactly, right? So we've got to get that it's going to send the composition of G and G dash exactly to the, we have to have exactly the image of the composition is the composition of the images, and also that the image of the identity arrow is the identity arrow of the image. But with a pseudo functor, we don't require these kind of identities to hold exactly. We allow them to hold up to a sort of invertible 2 cell in the target, in this case cat. And these sort of two cells which tell us how how these laws almost hold, the sort of fiddle factors, if you like, have to satisfy certain coherence conditions that I'm not going to get into at the moment. If you have a look at the Handbook of Categorical Algebra, Volume 1, Chapter 7, these ideas are all explained there. But basically, it turns out that there is a notion of opfibrations of B, and it's kind of like a generalization of the notion of discrete opfibrations of B. So remember, if we have like a general functor P from E to B, there's certain conditions under which that kind of thing can be regarded as a discrete opfibration. Well, it turns out that there's also kind of more general conditions under which such a functor can be regarded as an opfibration. And so we have a category of opfibrations, and it's this subcategory of cat slice B. It's a full subcategory of it on the functors of this kind of form, which satisfy the conditions of being opfibrations. And I'll give you definition of opfibration very shortly. So the idea basically is not that complicated. It's just that we have the situation from before, and we're sort of generalizing both sides. So we're generalizing from discrete opfibrations to something called opfibrations on the right-hand side, and on the left-hand side, rather than looking at these co-presheaves, we're looking at these pseudo-functors into cat. So I think this is the category that has objects as pseudo-functors into cat, and arrows as pseudo-natural transformations, which are like natural transformations, but rather than like having the commuting squares exactly, there's these like invertible two cells of cat, which do the job. So I'm trying not to get into the details of this too much, but I wanted to sort of explain this very beautiful idea, because really the point of this, in my opinion, is that it's kind of like, how with the discrete opfibrations, like I was saying, like really the key is this idea of the elements category. And yeah, there's some elaborate definition of when a functor into B is considered a discrete opfibration, but really the point is that definition is to sort of tell you when something looks like an elements category. And in a similar way, an opfibration is kind of like something that looks like a projection from a Grothendieck construction. It's just that Grothendieck construction can be like based on a pseudo functor. So okay, that's a lot of information. Like the point really is just that we're generalizing this to this, and we're generalizing this to this, and now I'll tell you what this is. So I'm going to now tell you what the definition of an opfibration is. And here it is. So, well, we're going to start explaining what it is. Why is this relevant? Well, I mean, it's relevant because this is a very nice structure, but also, like, the title of this video is Fibrations, right? And now I'm going to give you a definition of an opfibration. And basically, we're going to see very shortly that we can just dualize everything that we've done, and we're going to get this kind of picture here. So the dual notion of an opfibration is a fibration, and everything's going to work out. So really the main thing that we have to do now is just to understand what an opfibration is, and then pretty much we'll have all the knowledge we need to understand lots of things about these structures. So what is an opfibration? Well, before I define that, I want to define something else, which we're going to need, and that's the idea of a co-Cartesian morphism. So here's the idea. Suppose that we have a functor P from some category E to B. Now, you should probably think of E as like the Grothendieck construction of some functor F. So this is like our total category, but you don't have to. Let's just think about this abstractly. So this is just a definition. We're saying that we have a functor P like this, and now we also have an arrow phi, which is in this total category E here. It's in this category E, which we could call total, but so now we have this arrow phi, which is in this category E. And what we're saying is that under certain conditions, this arrow phi is considered to be something called co-Cartesian. And it's called co-Cartesian when this stuff here is true. So what's this stuff here saying? Well, what it's saying is that when we have any kind of psi, which in some sense is similar to phi in the sense that it has the same source, and also when we have any g, which has the property that if we do g after p of phi, that gives us p of psi. Well, in that case, there's going to exist this unique arrow chi, which has the properties that p of chi is g, so it's getting sent to g, and also that it makes this triangle commute. So it gives us a sort of way to emulate this phony arrow psi here. And that's it. That's the definition of when this kind of phi here is co-Cartesian. So I'm just going to push forwards and finish the definition of an opfibration now. So now we have this idea of co-Cartesian under our belts, or at least, now we've seen the definition, we can define what a opfibration is. So an opfibration now is going to be just a functor from some category E to some category B, and it has to have the property that if we pick any object of E and any arrow coming out of P of E, then there's going to exist a unique co-Cartesian morphism with respect to P that gets sent to that arrow F. That's it. That's our definition. And so that's our definition of an opfibration. And now we have that this category here, opfib of B, is just going to be like the full subcategory of cat slice B on the opfibrations. And you can see that discrete opfibrations are special kinds of opfibrations, much like the elements category is like a kind of special case of a Grothendieck construction. And so hopefully this picture now is starting to make sense. So now we have all this lovely structure. Let's just dualize things. And here's where we go from opfibrations to fibrations. So honestly, like, there's a couple of things to say here. Like, I think that opfibrations are simpler because they don't involve contravariants so much. So, for example, here we have a covariant functor from B to cat. Here we have a covariant functor from B to set. Opfibrations are like that. They involve these covariant functors, which basically makes them simpler. On the other hand, fibrations, which are the sort of jewel of the concept we've been looking at so far, are more abundant in mathematics, and in some sense you could say that they're more important for category theory. So it's going to be very worthwhile to understand how we can get to the idea of fibrations. Now, basically, in some sense, it's pretty simple. We're just looking at the dual of the notion, but since what we have here is some fairly complex machinery, the way that this duality works can get a bit elaborate. So I'm going to spend the next few minutes describing how we can kind of use duality to go from this picture of opfiberations to the picture of fibrations. And after that, I'm going to sort of stand back and look at fibrations from their own perspective. And at that point, things will get a lot simpler, and we can look at like fibrations, which have really been the target of this video all along, really, because they provide a great deal of sort of organizational power. So we want to dualize this stuff. So we want to dualize the notion of a opfibration. Let's start with that. So the dual of the notion of an opfibration is something called a fibration. And so what we say that a functor P from E to B is a fibration if and only if the opposite of that functor, so we could call that P op, is an opfibration. And what's the opposite of a functor? I'll remind you, if we have a functor P from E to B, then its opposite, well, it's going to go from E op to B op. It works the same way as P worked on objects, so it sends E to P of E and so on. But if we have an arrow K in our original category E, then we're going to have an arrow K op in E op. And what's going to happen to that under our functor P op? Well, it's going to get sent to the opposite of P of K. So this is how P op works. It basically sort of works the same way as P, but you know, the arrows are all reversed, that it's mapping. So this is the idea of the opposite of a functor, and the idea is that this functor P is going to be a fibration if and only if its opposite is an opfibration. So that's kind of enough. And now we can start to look at a picture like this, which is sort of analogous to the picture we were looking at before, but it's the kind of dual of it. So what we have at the bottom right here is this category of fibrations. And so if we have a functor E from P to B, it may be a fibration. And it'll be a fibration if and only if its opposite is an opfibration. But you know, you can get the conditions for P to be a fibration directly. Fibrations are also called Grothendieck fibrations. So if you have a look at NCAT there's a nice page which gives you a sort of explicit definition of what a fibration is. And, you know, you can talk about them in terms of Cartesian morphisms, which are the sort of duals of co-Cartesian morphisms and so on. So we kind of can understand what fibrations are. And then this category fib B is just going to be the full subcategory of cat slice B on the objects which correspond to these fibrations. So that's what these things are. What's going on in this picture at the bottom left? Well, that's pretty self-explanatory. These are just functors from B op to cat. Now, the interesting thing here, one sort of interesting thing is, how do we get from a functor from B op to cat to a fibration? And to do that, we have to do something called a contravariant Grothendieck construction. So this is a little bit funny when one first encounters it. So the idea is basically like this. We've already seen something that I've been calling the Grothendieck construction. I should really call this the covariant Grothendieck construction. And notice I'm writing GR of F to denote the Grothendieck construction here. Now, actually, this is not the normal thing that people mean when they talk about Grothendieck constructions. Much like fibrations are more popular than opfiberations, there's a sort of contravariant version of the Grothendieck construction, which is kind of more popular in a way. So for the contravariant version of the Grothendieck construction, what we have is we have a functor from bop to cat, and most people would say that's a contravariant functor from b to cat. And given such a thing, we can construct a category which we call GRO of F. And this is the so-called contravariant Grothendieck construction. And it comes with a projection P, which is going to be a functor which goes into the category B. So, like, warning here, this is not the same thing as the covariant Grothendieck construction. When one first sees this kind of thing, one might think, oh, well, I'll just look at this functor, I'll just define a category A, which is equal to bop. So now I have a functor F from A to cat, and I'll do the covariant Grothendieck construction that we already know on this functor from A to cat. If you do that, you won't get this. This is something different, okay? You can see that because, like, if we did this construction here, well, we'd end up with, like, the Grothendieck construction of F, and that would come with this projection functor into A. But actually, we want a projection functor into B, which is not the same thing. So, yeah, this is something new, basically. This is something new. This is the contravariant Grothendieck construction. If you have a look at this paper, I found this paper very useful in preparing for this video. Generalized Lens Categories via functors. This does a really great job of explaining the sort of difference and how you can convert between the sort of contravariant Grothendieck construction and the covariant one. But let me quickly explain what this contravariant Grothendieck construction is all about. So let's suppose that we have a functor F which goes from bop to cat. So some people call this a contravariant functor from B to cat, but whatever. What we want to end up cooking up is a category which is called GRO of F, and it comes with a projection functor that goes into B. So how do we do it? Well, it's all basically described here. The quick kind of picture to have in mind looks something like this. So the quick kind of picture to have in mind looks something like this. So we have this functor from bop to cat, which is called F. So if we have an ROG in the base category that goes from B to B dash, well, when we sort of apply this functor F, then like B dash is going to become this fiber category here, F of B dash. B is going to get sent to this fiber category F of B, and then G here is going to get sent to, or it's going to sort of generate this functor which we could call F of GOP, And that kind of goes in the opposite direction to G, right? Because really F is a contravariant functor. So like even though the arrow in the base category goes from B to B dash, the arrow from the arrow between these fiber categories goes in the opposite direction. It goes from the fiber category over B dash to the fiber category over B. And we can call this kind of functor F of G op. It's sometimes called G star. Sometimes this kind of thing is called a substitution functor. So this is the kind of data that we're dealing with. But what we want to do is to sort of take this data and sort of, in a sense, rub out the bubbles and stick things together so that we get a kind of big category. And that's going to be our contravariant Grothendieck construction. But it's a little bit tricky because we really want there to be a functor from what we get into this category B. So somehow we've got to sort of deal with the fact that this substitution functor's in a sense going in the wrong direction. Like if you don't overthink it, if you just follow the definition, it's pretty straightforward. So this is how this contravariant Grothendieck construction is defined. It has objects like before, which consist of pairs of an object of the base category and an object X in F of B. And then the arrows are as described here. So maybe easier to see this in a picture. So we want to think about what it means to have an arrow from B comma X to B dash comma X dash. And this is going to be an arrow of our contravariant Grothendieck construction of F. So such an arrow of this Grothendieck construction is going to consist of a pair, G and H. And now G is going to be an arrow in our base category here, which goes from B to B dash. And now H goes like this. So what's going on here? Well, we've got this object X dash in the fiber above B dash. And then this kind of substitution functor is going to send this to F of G of X dash. And then what we want to do is to have H as an arrow from X to this thing. So in a sense, X dash is getting sort of fired back into the fiber category over B, and then H is allowing X to connect to the image of that X dash. And that's what an arrow in this contravariant Grothendieck construction looks like. And then, you know, the way composition and identities work, it's sort of analogous to the covariant case. You can figure that out for yourself. But yeah, so what we have here really is just a sort of dual of what we had before. So we know what fibrations are. Now we know about this contravariant Grothendieck construction. And then what's going on up here, these things are just called discrete fibrations. So you can get these by sort of dualizing the notion of opfibration that we've already discussed. And then this is our category of presheaves. And then this is our sort of contravariant elements category construction. And if you take a look at chapter 2 of Emily Reel's book, Category Theory in Context, you can find out more about how you figure out the elements category with respect to one of these presheaves and all of this kind of stuff at the top here. Okay, so let's take a look at a really nice example of a fibration. So suppose that we have a category B and it has all pullbacks. So for any kind of corner consisting of a pair of arrows with a common target, we can find a pullback of that kind of diagram. So there are lots of examples of categories like this, like set, for example. Now, what we claim is that if we take the arrow category of B, then this functor that selects the codomain is going to be a fibration. So you could be a bit confused at this point because I've already sort of claimed that this functor is an opfibration. So how could it be a fibration and an opfibration? Well, it can be. Such functors are sometimes called bifibrations. And yes, cod is a bifibration in this case. But at the moment, we're just interested in what sense it is a fibration in. So how does this work? Well, basically what we want to do is to kind of find how we can get something like this arrow category as a Grothendieck construction. So what we're going to do is, we're going to consider a functor f from b op to cat, and the way that this functor works is it's going to make slice categories. So it's going to send an object b to this slice category, b slice little b. And the way it works on arrows is a bit funny because this has to be a contravariant functor. So if we have an arrow g from b to b dash, that corresponds to an arrow g op from b dash to b in script to b op. And then what this arrow is going to turn into under this functor f is this substitution functor here. And that's going from script to b slice b dash to script to b slice b. And the way that this works is by doing pullbacks. Okay, so if we have an object in script to b slice b dash, that's going to be an arrow in b dash. So there it is. And if we pull that back along g, then we get this arrow pi 2. And that's going to be the image of e under this substitution functor g star. So this is telling us how this functor works on objects. The way it works on arrows is kind of given. You can get it by thinking about the universal property. So then the idea is basically that if we take the contravariant Grothendieck construction of this f, then this is going to give us back our arrow category. So that's kind of interesting. So what's going on here? Well, this is really an example actually of a sort of application of a result from this paper here, or at least this is where I saw the result, framed bicategories and monoidal fibrations by Michael Shulman. So in result 3.9, he says that if you have a fibration P, it's going to be an opfibration as well, if and only if for every arrow in this category B, we have that this substitution functor G star has a left adjoint. And this is indeed the case for us because we've got like these slice categories here, and we've got this functor G exclamation mark that we talked about before that, you know, just sort of takes an object in this slice category like E here and replaces it with G after E. So this sort of post composes with G. And then we have this G star here, which is the right adjoint of G exclamation mark. And G star sort of takes objects in this slice category and pulls them back along G to get stuff like this. And so since G star has a left adjoint for every G, we can apply this result from Shulman, and it says that in this case we're going to have the our fibration is going to be a bifibration. It's going to be both a fibration and an opfibration. So that's a nice result. This whole fibration is pretty interesting. It's discussed a lot in Bart Jacobs' book, Categorical Logic and Type Theory, where I'm taking quite a lot of my material from there. And in particular, we can sort of look at a restriction of this setup to where we're using monomorphisms. So in particular, let's consider a new functor now from B up to cat. And rather than sending an object B to the whole slice category, let's send it to what we'll call this category of predicates. And what this is it's the full subcategory of this slice category on the sub-objects of B. And what do I mean by the sub-objects of B? Well, I mean that we look at the monomorphisms into B. So the objects of this thing are going to be arrows into B. Some of them are going to be monomorphisms. So we can take the full subcategory on those monomorphisms. Actually, let's cut down on the equivalent stuff. Let's just take one non-equivalent copy of each monomorphism. So then we've just got like just the sub-objects. So it's just a way to cut down on equivalent monomorphisms. So we have this that we could call the category of predicates of B, and this is what F sends little b to. And then again, when we have this arrow G, we get this substitution functor G star that just pulls back these sub-objects along G. So this is a nice thing. And this functor, again, we can look at the Grothendieck construction of it, and we've got all this kind of fibration stuff going on. And basically, we have situations that look like this. So if we take B as set, then we have this sort of category of predicates. This is discussed in chapter 0 of Bart Jacobs' book. And the idea basically is that, like, we have these sets and these functions, like this function length from words to numbers. Now, the category of predicates of n is going to have objects corresponding to the sort of subsets of n. For example, here's a subset. This is corresponding to the numbers that satisfy this property that they're even. And then if we have like a function, like this length function from words to numbers, we get this corresponding sort of substitution functor, which sends predicates on n to predicates on words. And to get how this works, we just look at this description of this sort of predicate or subset of numbers. This is the set of numbers where is even is true. And then we do the substitution where we substitute this number n for the length of a word. And now we get this kind of comprehension, which is describing a predicate or a sub-object or a subset of this set of words. And in this way, we're able to go from this sort of category of predicates over numbers, which we can think of as like the sort of lattice of subsets of numbers, to this lattice of subset of words. And we're sort of doing it by substituting. And this is a very rich sort of structure. And in Jacobs, they discuss how all sorts of things in logic can be obtained by thinking about this kind of category of predicates. And there's various different sort of adjoint functors and things that are related to this. So one more really beautiful example. Suppose that we take a category E, which is both complete and co-complete. Now, what we can do is we can consider a functor like this. I'll call it blank, comma, e. So what this is going to be is it's going to be a functor from cat op to cat. So the way that this works is that if we supply a category C, then we get this category of functors from C to E. And also, if in cat we have this functor K from C to D, well then we're going to have K op from D to C in cat op, and then this functor is going to send this to this functor K star, which is going to allow us to translate functors from D to E to functors from C to E. And the way that this this K star works is it basically takes a functor from D to E and it sort of precomposes it with this functor K here. Now, the lovely thing about this is that if you know about CAN extensions, you know that in this case, this functor here is going to have a right adjoint called rank, also a left adjoint called lan. And so again, we can apply Shulman's result, and it's going to tell us that if we do the sort of Grothendieck construction of this, that's going to be a fibration, of course. It's going to go into cat, but it's also going to be an opfibration. In fact, and so actually what we have here is a bifibration. In fact, I think it's actually something called a trifibration. Now, I've got to admit, this is a bit new to me and I haven't checked all the details here, so you've got to take this last thing I've said with a bit of a pinch of salt. But still, I think these kind of, if this kind of stuff works, it's very lovely because it's showing how all sorts of very immense structures are being organized in lovely ways by these fibrations. So, okay, so I've said a bit about fibrations, and as promised, this stuff does relate to these ideas of lenses. And so in particular, I'm talking about the ideas of Grothendieck lenses that I found out about from reading a paper by David Spivak. I shall put a link to it in the description. But basically, the idea is like this. Suppose that we have a functor from C op to cat. Now, we can take a Grothendieck construction of that. Maybe the most direct thing to do would be to use the contravariant Grothendieck construction, but that's not what we're going to do. We're actually going to think of this as a covariant functor. So that's fine. We can just define, say, category D to equal C op, and then think about this as a covariant functor from D to cat. And so we can perform the covariant Grothendieck construction on F. And then we're going to take the opposite of that. And that's what we define as the category of lenses of F. And also this thing comes with a projection functor, right? Because like the Grothendieck construction of F is going to come with a projection functor which goes into D. And so if we take the opposite of that, we get this functor that goes into D op, or That's the same thing as C. So this is what we have. This is our category of lenses. There's loads of different kinds of lenses that people study, and a lot of them tend to live in categories like this for some kind of a functor F from C-op to cat. And I want to relate this quickly to the ideas, and so I want to show you quickly how we can get some perhaps familiar lenses, if you've seen them before, from this kind of approach. So I'm just going to quickly go through this. Basically, if you look at this construction, like, you can spend quite a long time sort of untangling it and seeing what this category ends up looking like. And you end up finding something like this, that this is going to have objects as pairs of an object of C and an object X of F of C, and then an arrow from C comma X to C comma X dash is going to consist of an arrow from C to C dash. That's going to be our get. And then also this arrow H, which goes this way. That's going to be our put. And I'll just scan over these pictures that show you how to do composition. You can pause the video if you want more details. Actually, I'd recommend checking out Spivak's paper. It's very clearly written. So how do we use this idea to get at some simple sorts of lenses? Well, do you remember this functor here that we encountered earlier? This is the sort of contravariant functor that makes slice categories. So this is this contravariant functor from beta cat that we saw before. It sends objects of B op to these slice categories. If we have an arrow G of B, then the sort of corresponding substitution functor is basically going to work by pulling stuff back along G. Incidentally, the way this substitution functor works on arrows, I didn't mention it before, but I'll mention it now. So if we have an arrow H from E to E dash in this category, then when we apply this substitution functor G star, we're going to get this arrow here, which is the unique one that makes this diagram commute, where these things here are pullbacks. So there's a theorem in McClarty about this, theorem 4 point something, maybe 4.9. And so, yeah. So anyway, if we take this functor, well, let's use a category called C instead of a category called B. And so we have this functor here. Let's call this functor the slice functor. And it turns out that if we then get this category of lenses of this slice functor using this construction I was just talking about, so basically we're talking about doing the covariant Grothendieck construction on slice and then taking the opposite of that. Well, it turns out that gives us this category of so-called dependent lenses. And the objects in this category are going to consist of pairs of an object C and also an arrow X, which goes into C. So they're going to be what the objects of this category, and so they're going to be what the objects of this category look like. And then it turns out that if you restrict your attention to the objects of this category here that have the form that they consist of a C and a projection from C times Y into C, so that would be a projection pi 1. Well, if you look at those kind of objects and you look at the full subcategory of this category of dependent lenses on these kind of objects, then it turns out that that gives you this category of then it turns out that what you get is this category of so-called simple lenses. So basically we can think of this as having objects as pairs C comma Y, and then the idea is that a morphism from CY to C dash Y dash is And then the idea is that a morphism from cy to c-y' is going to consist of a sort of get map which goes forwards, and then this sort of put map which goes from c times y' to y. So basically, if you do all of that fancy Grothendieck construction thing, and then if you do all that kind of fancy Grothendieck construction thing using that slice category and pullback based functor we were talking about before, and then you sort of restrict it to these particular objects, you end up getting this lovely category of simple lenses. And the sort of notion of how you compose like one of these get put arrows with another get put arrow is sort of baked into that. So I'm really just sort of tiptoeing around the outskirts of a very vast subject, which is this subject of lenses. And so if you want to get more into this, I recommend David Spivak's paper. Also, David Jasmeyer's has lots of nice material on open dynamical systems that you'll see backs onto these kind of ideas.